All right, multidimensional motion. I'm going to go through the packet here. I'm not going to provide written solutions at this time. I have these written up somewhere. I need to find them and I'll get them posted at some point. But I'm going to do them on the board in class now for these guys here. And you can follow along, all right? So the main point in multidimensional momentum is that momentum is conserved in the x direction and the y direction independently. All right? So you got to be organized. You know, I recommend you make a drawing whenever you're doing momentum problems. Kind of get your brain going, visualize what's happening. All right? So this first one. We've got a billiards ball, 0.15 kilogram, traveling at 7 meters per second. It's another billiards ball, initially at rest, and deflects at an angle of 15 degrees at a speed of 5 meters per second. So let me draw the setup here. So we've got the first billiards ball coming in, 7.0 meters per second, mass 0.15 kilograms. All right, try to close this video so you don't hear this door, so I don't get a bleed from across the hall there. All right, so this billiards ball is at rest, right? Well, when they hit, let me color this one like a ball. You know, when they hit, the word deflect, that's talking about the incoming ball. All right, when you hear the word deflect, that's something that's moving and then its path gets changed. Right? So when you hear the word deflect, that's how you have to think about it. So the white ball, when it hits, let's say it collides here, flies this way. So if you think about a coordinate system here, this angle is 15 degrees. All right? And now it's traveling at 5 meters per second. And the question is, okay, what happens to this ball? What is the velocity and what angle does it make when it flies off? All right. So this is kind of before the collision. One ball is going in a straight line. The other ball is at rest. After the collision, they both fly off. Now we know this ball is going to fly up because of conservation of momentum. This ball deflects downward, so it has a vertical momentum down. This ball has a momentum, vertical momentum up. So, how do we go about doing this? Well, we break this into x and y direction. All right, we say P, now the subscripts here can get really busy and hard to follow. So I'm going to call it P initial and P final, or P before, P after. The I and the F actually work kind of nice here because, you know, we're not dealing with A and B and 1 and 2. So the initial x momentum, total, and you can think of this as a vector quantity if you want. And this is a sum of all the momentums as well. This is the total initial x momentum. Must equal the total final x momentum. Now you don't need to use those vector symbols, but you do have to know that it is a vector quantity. The velocities are met. Velocities matter. Now I'm going to call this ball 1 and 2. All right. So that means, you know, the initial x momentum of ball 1 plus the initial momentum x of ball 2 has to equal the final x momentum of 1 plus the final x momentum of 2. All right? Now, the initial x momentum of 2 is 0. So, all of the initial momentum, why is this one 0? Well, because it's not moving in either direction. Right? So, its x momentum is 0, so is its y momentum before the initial. Now we can start plugging stuff up in here. One thing that's kind of nice is if I do it in variables, so I'll say V initial for ball 1, M1, V initial 1, equals M1, V, you know, technically there should be X's on those subscripts. again, I said the subscript's going to get kind of crazy here. So I have M1 V initial x of 1 equals M1 V final x of 1 plus M2 V final x of 2. So I'm keeping track of momentum in the x direction. Now what's true about, in this problem, what's true about M1 and M2? Yeah, they're equal. Right? They're the same mass. So mathematically, you can actually cancel out all the masses here. You can't always do that, so that's why I showed the m's in here. All right? So now we can start to figure some stuff out here. All right, so the initial x here is 7.0 meters per second. And it's positive the way I drew the coordinate system here. The final x, well, how do I get the x velocity of this ball here? All right, so this ball, I have to take that velocity, that 5 meters per second, at an angle of 15 degrees. I'm going to have to break that velocity into x and y components. So the initial x1 is going to equal to 5 meters per second times the cos of 15 degrees. The initial y is going to equal 5 meters per second times the sine of 15 degrees. But I tell you what, it's almost easier just to leave this one in terms of v rather than putting in the number here. This one. Anyhow, let's go ahead and calculate those two. All right, the initial x is 5 times the cos of 15. All right, the initial y is 5 times the sine of 15. All right, oops, do the math there. So I've got 4.8 and 1.3 for the x and y velocities. Now, this y velocity is down, right? So I am going to have to make that negative here, okay? So now back to our conservation of momentum problem here. All right, this is ball 1. I am going to look at ball 2 here in a second. All right, so V final x1, I know what that is. That's positive 4.8 meters per second, right? So therefore, plus V final x2, I know what that has to be. Right, so now V final x2 is going to have to be 7.0 minus 4.8, or what is that, 2.2? So V final x2 has to equal 2.2 meters per second. So that ends up, so that's the x component of the second ball's velocity. So ball 2 now I know has an x component of velocity of positive 2.2 meters per second. So ball 1 has given some of its forward momentum to ball 2 when it hit. All right, and the mass is canceled out. So that's for the x direction for each object. Now we've got to look at the vertical direction here. Okay? We've got to look at the momentum in the vertical direction. So momentum in the horizontal direction was conserved. Now we've got to look at the vertical direction. All right. So in the vertical direction, again, put this down. I don't know why I'm holding it under my arm awkwardly. I guess I'm not exactly doing the questions as written. I'm kind of going through to get to the final answer here. F. I'm not following parts A, B, C, and G, and E. Oh well. All right. So for the other ball now, for the other direction, we say P initial Y equals P final y. So again, the initial y, that's got to be the initial y momentum of that ball. And since that is moving in a straight line the way I drew it, this is actually going to be 0. The initial y momentum of this ball here is 0. It's not moving vertically. It has no momentum vertically. The final y is going to be m1 v final y1 plus m2 v final y2. Alright? So these two, their momentums, this is the reason why they split, right? Their momentums in the y direction have to be equal and opposite. So well, we'll see what happens here. I am looking for this, v final y2. I already figured it out with v final, oops, I labeled this incorrectly. It should have been final back here. V final, x1, v final y1. I already know v final y1. So when I solve this, I got to bring this over here. I'll say, actually I'll bring that over there. M1 v final y1 equals m2 v final y2. The m's again cancel out because of the same mass. And if you had the masses, you would still divide one over to the other side, right? Solve for the velocity. So v final y2 has to equal negative v final y1. It's going to equal negative of negative 1.3 meters per second. V final y2 equals positive 1.3 meters per second. Because of the same mass, they're going to both go vertically the same velocity. So now I know this one's final y velocity, positive 1.3 meters per second. So the final question here is determine the speed and direction of the motion of the second ball. Right, well, that would be this. The final speed of this ball is actually the magnitude of the velocity vector combined. So the actual speed of this ball is traveling upwards, and actually it's going to be greater angle here, right? Or no, never mind. So v equals the square root of 1.3 squared plus 2.2 squared. The second square root of 1.3 squared plus 2.2 squared equals about 2.6 meters per second. All right, then I need an angle. Now the angle is relative. Typically we would look for that angle relative to the x-axis. So theta is going to be 10, and this comes out to 6 meters per second. Tan inverse of opposite over adjacent, 1.3 over 2.2. Second tan of 1.3 divided by 2.2 is about 31 degrees. All right? So that's typically kind of what we're looking for here. So the final speed, I'll redraw it over here. The final speed and direction of motion of the ball that was hit by the incoming ball. So the final kind of report is that ball 2 is going to head off at 2.6 meters per second at an angle of 31 degrees above the horizontal, like that. All right, so momentum is conserved in the x direction and the y. All right, the next one, it's kind of a fun one. It kind of defies, reality. We're doing just two-dimensional momentum right now. A waterproof firecracker is molded into a small 30-gram block of plastic so that the wick is exposed at the top. Video camera is used to perform video analysis. After the firecracker explodes, the students find 3 pieces which fit together perfectly to form the original block. So somehow this divided up miraculously into 3 pieces. Alright? And also, they have the same mass, so that makes it even more miraculous. So this puck exploded into 3 equal mass pieces. Right? So got this puck, somehow explodes, 100 grams, 100 grams, 100 grams. Alright? And unfortunately, the clumsy physics student that lit the firecracker ran into the tripod, moving the camera so that only 2 pieces are seen flying off in the video. To perform an analysis, it's determined that 1 piece flies off at 150 meters per second, and a second piece flies off at 210 meters per second. So I'll say this one's 150 meters per second. This one flies off at 210 meters per second. And the angle between the 2 pieces is 110 degrees. Determine the speed and direction of motion of the third piece relative to one of the other pieces. Include a diagram. All right. So the third piece, we know it's probably going to fly off kind of like this, right? You know, it's probably going to be a velocity in the same, range as those velocities. 360 degrees total all the way around. You divide that by 3, that'd be like 120. So, the angle here, one of these probably is going to have to be a little bit bigger, So you kind of logic through the kind of conceptually should head off that. So the question becomes, okay, so how do we set this up? How do we set this up? We got to set up a coordinate system first of all. Are any of these obviously 90 degrees apart? No, not really, right? So the way I drew it almost looks like it is 90, but I should probably make it a little more like that, right? So I'm just going to pick one of these given velocities and put it on an axis. All right, so I guess I'll put that 150 on my x-axis, and then I'll assign a y-axis kind of like this, right? So if this is 90, right, what does this then have to be? 20. Yeah, that's going to be 20 degrees relative to the y-axis. All right, so I'm going to kind of redraw this a little bit so it makes a little more visual sense. Right? The coordinate system doesn't matter, right? It's selectable by you. So I'm going to kind of think of this a little bit differently than the way I initially drew it, right? I'm going to say, okay, I'm going to change my coordinate system to be nice and vertical. All right. So that one mass is flying off this way. Okay, it's going to fly off that way. I'm going to make that to 150 meters per second. All right, that's this particle exploding off. Its mass is 100 grams or 0.1 kilograms. Now, I'm going to make that 210 one go like this. Make this 20 degrees. 210 meters per second. All right, another 0.10 kilograms. All right, then the third one, it's going to fly off maybe this way or something. So that's our, all right, B3 is our kind of our big unknown. So we attack this now by, going through the conservation of momentum. All right. I attack this by going through the conservation of momentum. So I'll say in the x direction, all right, P initial x has to equal P final x. What's our initial momentum of everything here? 0, because everything starts off at rest. So for all of these, it's 0. All right. P final x here, well, I'll start with this one because it's going to be just, and I don't write all those variables out. like those subscripts like I did before, you don't need to write all that out with the variables. If you know everything's velocity, you know, if you know a lot of the velocities and mass, it is beneficial with the masses in this case because there's going to be cancellation of the masses again, but I'm just going to do it. So this is, you know, I'll call this particle 1, 2, and 3. So this is actually P final x of 1. All right, 2, all right, so plus 0.10 kilograms times, this is going to have to be P final x of particle 2. How do I get the x velocity of particle 2 here? That's the trick, right? It's going to be this component. So it's going to be 210 meters per second times the sine of 20 degrees. Now, of course, I'm running off the board here, so that's unfortunate. I'll move this over a little bit. It's a mistake I made last time, trying to move that over. All right, got a little room there. Let me see. Yeah, that's about it. So I'll just write it below here. Plus, you know, this will have to be the x momentum of the third piece, right? So this is the x momentum, px2, px3. And this needs to be negative, right? My x component of the second particle's velocity. All right, so the third particle now, we've got 0.10 kilograms times, well, we don't know what that velocity is. We're going to call it just Vx3. Not even going to put final on it. I'm just going to call it Vx3, the x component. So that's what we're looking for now, Vx3. So it's a little bit hard to see here. The masses are all going to cancel out. We get 0 equals positive 150 meters per second minus 210 times the sine of 20. I might as well calculate that now. All right, 72. So that's ends up being 72 meters per second plus Vx3. All right, so easy math now. Just move everything over to that side. So we get negative. We get, well, I can do this math first. 150 minus 72 is 78. Bring it over there. We get negative 78 meters per second equals the x velocity of particle 3, that should be. All right, so particle 3, right? I'm going to keep track of it over here. I'll draw it. Particle 3, we know it's going to fly with the x component of its velocity of negative 78 meters per second. So now we've got to go back through the y direction. All right, and this one's a little bit easier because we don't have a y. We don't have a y coordinate for a y component for this force here. So the initial y equals the final y. All right, it's a y. This is 0. The final y here. We are simply going to have 2 and 3. So we're going to have 0.10 kilograms times, so this is 2, the y component 2 times 210. It's going to be negative 210 times the cos of 20 degrees plus 0.1 kilograms times V3's y component. All right, so 0.1 times negative 210 times the cos of 20. All right, that's negative, oh, I guess the masses cancel out here. right? So do that, negative 197 plus d3y. So d3's y component is positive 197 meters per second. I guess I should make it just 200, right? Two sig figs. All right, so then this component is about 200 meters per second. And then we're looking for the speed and an angle. Now, it says relative to one of the other plots. Well, I'm going to find this angle. We'll call that theta 2. So if I find this little angle here, I just have to add 90 to it. So I'm going to find this angle here. So the magnitude of the velocity here is going to be square root of 200 squared plus 78 squared. That's going to be 215 or so. All right, so that's 215 meters per second. The angle theta equals tan inverse of opposite over adjacent, so 78 over 200. Second tan of 78 divided by 200 is about 21 degrees there. So that's 21 degrees. To get back to that 90. So it would be about 110 also.